Rownak, please go ahead.
Good morning, everyone, and thanks for being here. Today, I'll be presenting my research on Mavic, a self-programming, self-propagating streaming accelerator for AI computing. This work is being conducted under the supervision of Dr. Mustafizur Rahman. Here's a quick introduction of myself. My name is Rownak Chowdhury, and I'm currently pursuing my PhD in Electrical and Computer Engineering at UMKC. I work here as a graduate teaching assistant. This is a brief outline of today's talk. At first, I will begin with the motivation and background behind our work. Then gradually, I will move on to the hardware architecture, on-chip memory, data propagation, data mapping, followed by the benchmarking results. Over the past few years, AI has evolved from a set of experimental algorithms into the backbone of almost every modern application. As AI's intelligence grows, so there is hunger for data, computation, and efficiency. But this raises an important question. Does our current hardware truly understand AI's way of computing? Or put differently, why does AI computing demand a new hardware paradigm? What limits today's hardware from scaling with AI's complexity? These questions have led to the emergence of domain-specific hardware development. And that's exactly why we are seeing a new wave of a specialized AI chip. Now, let's take a look at how the hardware landscape is being redefined. On the left, almost every major tech company has now built its own custom AI accelerators. NVIDIA with its A100 and H100 GPUs, Google's TPUs, AMD's Instinct series, Intel's Havana and Nirvana, and specialized startups like GraphCore, Cerebras, and Grok are purely focusing on AI acceleration. All these architectures are based on a fundamental principle: trade some flexibility for massive efficiency gains. On the right, this trade-off becomes clear. CPUs are highly flexible, but they're inefficient for deep learning operation. FPGA and GPUs improve performance through parallelism. An ASIC sitting at the top deliver the highest performance, but at the cost of programmability. So as we move from CPU to ASIC, we gain speed and throughput, but we lack adaptability. And that's the core challenge today. How can we bring together the flexibility of reconfigurable platform and the efficiency of ASIC in one unified architecture through a smarter control, data, and memory coordination? And this challenge, balancing flexibility with efficiency, is exactly what led us to design our own accelerator architecture. But before diving into the detail, let's first understand why existing accelerators still fall short. Even though modern accelerators deliver massive arithmetic throughput, their end-to-end performance often falls short. That's because performance today is not just limited by arithmetic, it is bounded by control, locality, and orchestration inefficiencies. Let's unpack them. First, host-driven control limits concurrency. Many accelerators still today depend on host CPU to issue instruction and execute operation. This centralized control model introduces latency, and as a result, the fabric cannot continue execution autonomously. So yes, can the fabric itself sequence execution on the fly? Next, frequent off-chip transfer break data locality. Between layers, data often shuttle back and forth to DRAM, wasting bandwidth and energy while breaking temporal reuse. So the question becomes, where should operands live between layers to minimize movement? And finally, separate data and instruction pods cause stalls. Many accelerators stream control and computation separately, which may lead to ideal cycle when synchronization breaks. So we ask, can data and control be co-streamed to reduce orchestration overhead? These three challenges together motivated our solution, messaging-based adaptive vector computing architecture, or MAVIC, which unifies control, data, and memory into a single coordinated streaming model. So with these limitations in mind, our goal was to develop a computing fabric that doesn't wait for control, keep data close to where it is needed, and execute operations autonomously and efficiently. To achieve these goals, we developed a full stack solution that connects compute, memory, and software in a message-driven execution model. At the architecture level, we developed a lightweight message-driven microarchitecture with its own minimal ISA, enabling distributed execution without host supervision. At the memory level, we proposed a data type-aware 3-tier on-chip memory hierarchy that co-locates compute and memory to overcome the AI memory wall. For data mapping, we built a special temporal mapping and scheduling framework that systematically exploit multi-level reuse with high parallelism and utilization. And finally, to complete the pipeline, we developed the Intuit framework, an intermediate software layer that bridges ML compiler and Mavic hardware by generating binary executables and enabling automated benchmarking across different AI workloads. Together, these contributions form a tightly coupled compute memory mapping framework that advances the current limits of AI accelerator design. These ideas have already been translated into multiple publications and ongoing work. We have published few papers, including journals and articles, where we detailed our microarchitecture and memory hierarchy. Some manuscripts are under review, where we detailed our mapping framework, distributed streaming model, and hardware-aware scheduling approaches. Current ongoing work focuses on the Intuit framework for neural network mapping and also a cross-layer application for bioinformatics acceleration. And we have few more ideas in our pipeline. In this section, we'll discuss about the hardware architecture, where I'll cover messaging-based intelligent processing, message-driven parallel execution, deterministic execution model, and many more. This is a typical system-on-chip architecture of an AI accelerator, and it has multiple components like processing element array, L1 global buffer on-chip memory, L0 register, off-chip memory, host processor, some I/O peripherals, and host and accelerator section communicates via PCI. Our contribution here in this section, processing element array is decentralized compute fabric where thousands of nodes self-propagate computation deterministically. And to explore this further, we have framed this section around few guiding questions, like how can control live within the data itself? How can thousands of processing elements think, route, and compute on their own? How we have replaced control signaling with our deterministic execution model, and how we are achieving the programmability. Underlying our processor, there exists a novel computing technology which is inspired by the message passing in a human chain. For example, if there are 5 people in a line and person 1 wants to send a message to person 5, then person 2, 3, and 4 can from that bridge to route that message. This source destination based computing can be applied to computing core as well. To bring this idea to life, the fundamental unit of Mavic is a 64-bit message, which incorporates 5 different fields: present opcode, present destination, value to be stored or operated upon, next opcode, next destination. And to perform the deep learning operations, this is our instruction set architecture. With this instruction set architecture, we are capable of doing programming in the operation. Important thing to notice here is that for each arithmetic operation, addition, subtraction, multiplication, and division has 2 counterparts. One is directly performing the operation and storing it in the processing element, and other is performing the operation and streaming it to another processing element. Overall, messages fuse computation and communication, enabling decentralized execution beyond conventional control-driven architectures. This is a high-level overview of our Mavic microarchitecture. At the system-on-chip level, Mavic accelerator communicates with the host via PCI. Inside the accelerator section, Mavic follows a hierarchical organization: quad, block, tiles, sitemps, sitehost. One quad is equivalent to 16 tiles, to 56 sitemps, and 4096 sitehosts. Now, if we look into the tile structure, there are 16 sitemps. And if we drill down the sitemp microarchitecture, at every sitemp row, there is a vertical bus, there is a horizontal bus, and every column, there is a vertical bus. Vertical buses are useful for spatial multicasting, and horizontal buses are useful for spatial reduction. Now, inside every sitemp, there are 16 sitehosts. If we look at the sitehost microarchitecture, there are 4 ports: top, left, down, and right. Inside cyto microarchitecture, there is a message decoder unit, floating point arithmetic unit, message generation and dispatch unit. Cytos are capable of performing both computation and message passing. Associated with every tile, there is a L2 memory, on-chip memory. Associated with every cytem, there is a L1 on-chip memory, and associated with every cyto, there is a L0 embedded cyto memory. We'll discuss those things in details at section 3. To summarize, a hierarchical compute fabric unifies task distribution and data propagation and scale parallelism. Now we'll see how the message generation happen within the fabric. Many different versions of messages can come from the host processor. For example, for the same opcode program, value can be different. It can be filtered or it can be zero based on the role of the hardware columns. For non-reserved column, it is filtered. For reserved column, it is zero. I'll give you the idea of non-reserved and reserved column after a few slides. For multiplication, the pattern can be different. For 1 into 1 convolution, all bit will be zero. For other convolution, there is a specific pattern like T string, shift 2 bits, and identity for resonant like architecture, and some bits are unused for feature extension. Whatever messages come from the host processor, they will incorporate those fields: present opcode, present address, filter, image values, next opcode, next address, convolution pattern. First thing, what we'll do is using the present opcode and present address, we'll multiply, filter, and image values, and we'll perform some accumulation operation. As soon as the multiplication and accumulation operations are completed, we'll concate the result with the next opcode, next address, with an convolution pattern, and we'll generate an intermediate message. The key thing to notice here is that the next opcode and next address of the incoming messages are now the present opcode and present address of the generated messages. The calculated results are coming at the failure field. Convolution pattern, it may change or it may remain the same based on the flow of the computation. To illustrate that idea, we are taking a small example. Let's say we have a incoming message, present opcode is program, present address is 0, value is 1.1. So with this message, our expectation is that at cyto 0, value 1.1 will be stored based on this present opcode. So this is our cyto 0. So when the present opcode is program, present address is 0, value 1.1 is being stored here. And internal register will also store next opcode and next address. Now the second message, incoming messages came. Present opcode is multiplication, present address is the same as cyto 0, and the value is 2. So as soon as the present opcode, multiplication, and present address 0 came, it performs the multiplication operation and generates 2.2. Now using these three values, multiplication result, next opcode, which is already stored inside the register, next address, which is already stored inside the register, generating new messages. Again, the present opcode is coming from the next opcode of the incoming message. Present address is coming from the next address of the incoming message. Before finishing this slide, so what happens in the conventional control-driven architecture? So at first, they perform multiplication, then they keep this value inside the on-chip memory, then host decide how they will use it. In contrast, in Mavic, within the host, we are generating the message and we are self-propagating the next task. To summarize everything, each cyto is acting as a self-driven computing node which can decode, execute, and regenerate messages for fully autonomous data flow. Now we'll scale up the idea to understand the parallelism. Let's say we have 4 cytos, cyto 0, cyto 1, cyto 2, and cyto 3. This is the first 3 incoming messages, message 1, message 2, and message 3. If you look at their structure, the opcode is present opcode is program, address are 0, 1, and 2, and values are 1.1, 1.2, and 1.3. So that's why these values are being stored at their respective cytos 0, 1, and 2. Then the next 3 messages come 4, 5, and 6. Their opcode is multiplication, address is same, and values are now 1, 2, and 3. So we are expecting to multiply 1 with 1.1, 2 with 1.2, 3 with 1.3. As soon as the multiplications are being completed, it is streaming 3 new message. When it is streaming 3 new message, the present opcode is coming from the next opcode of the incoming message. Present address of the intermediate message is coming from the next address of the incoming message, and those values are the multiplication results. Now inside the fabric, those intermediate messages will perform automatically. So for this message at Cyto3, it will update the Cyto3 with value 3.9. For the next one, with 3.9, it will add 2.4. We'll get 6.3. And then for the next one, we'll get 1 point. We'll add 1.1, and finally we'll get result 7.4. So overall, here we are achieving a massive concurrency by executing thousands of Ps together and propagating messages in parallel, and everything is happening without the central control. If we look at the computational flow of the deep learning inference operation, for example, I have added here a ResNet 50 architecture. So after training, we already know weights and biases, and if we look at the structure of the neural network, there is a specific pattern. For example, here at first there will be some input image, and then we'll perform some convolution. Inside convolution, there will be a series of element-wise multiplication followed by accumulation. After that, we'll perform activation operation. Then we can perform different kinds of pooling operation, comparison or average. Then for FC layer, we'll perform some matrix multiplication, and then finally we'll get the output. So the point I want to emphasize here is that deep learning inference is structured enough to pre-plan task sequencing, forming the basis of deterministic execution. Now let's look at the task execution and routing together. So for routing, we'll try to answer this question: how do present address and next address steer result across cytos? And for task execution, we'll try to answer how do present opcode and next opcode sequences arithmetic across cytos. For this, we'll consider that hardware grid. In this hardware grid, there are multiple cytums. You are already familiar with cytums. Each cytum has 4 cross 4 cytos. And our problem is convolution, which will do multiple multiplication and followed by accumulation. So what is active columns? First 3 columns we are considering here as active columns. Every first 3 columns of each cytome. And the last columns are the reserved columns. However, it is not rigid. It depends on the software, and we can vary it according to our computation problem. Present address calculation is very easy. So there are RP number of hardware rows and CP number of hardware columns. So using this equation, we can easily calculate the present address. Now, the next address of the active columns C0 can be calculated using this equation, and their role is to perform multiplication parallelly. The next one, C1 columns. Their next address can be calculated as with this equation, and their role is to perform column-wise addition. Then C2 columns, their next address can be calculated using this equation, and their role is to perform depth-wise addition. And finally, the last column of the hardware grid, C3 columns, their next address can be calculated using this equation, and their role is to perform one more addition, that is multi-depth addition. The key I want to highlight here is that during routing, if you look at the addresses, next address of C0 is the present address of C1. Next address of C1 is the present address of C2. Next address of C2 is present address of C3. Similarly, for task execution, next address of C0 is equivalent to present address of C1. Next address of C1 is equivalent to present address of C2. And next address of C2 is equivalent to present address of, present opcode of C3. So we are maintaining a chain to propagate the message in a structured way. So as a result, address and opcode fields are co-defining routing and compute order, and it is ensuring precise data flow across the array. So now you have idea about the present address, next address, present opcode, next opcode. You can definitely generate some messages, but when you are generating messages, you need to schedule them in a way so that entire operations can be pipeline. We'll discuss that pipeline at section 4. I'll finish that slide with a key takeaway, that is Mavic enables overlap of compute, communication, and control through message sequencing under deterministic execution model. Now, what is the deterministic execution model? We have already seen the present and next address fields defined on chip routing. We know deep learning inference is structured enough to predict present and next task ahead of time. And we have also seen the hardware microarchitecture where Cyto decodes incoming messages, performs operation, and autonomously generates new messages. From the first point, we can develop a deterministic spatial plan. From the next one, we can develop a deterministic temporal plan. And this one gives us the idea of reconfigurable nature of our hardware architecture. So using these two deterministic spatial and temporal plan, we'll compile message stream to perform neural network inference in the Mavic fabric, and we'll send those messages from the host processor. When the host processor are sending these messages to the reconfigurable unit, it is self-propagating execution by generating new messages without host supervision. Overall, spatial temporal planning and reconfigurability are enabling deterministic host-free execution, and it is breaking the traditional load store paradigm. So when we started this work, the problem that was in our head was centralized control and static scheduling are restricting concurrency and flexibility. Our vision was to enable a distributed concurrent and deterministic execution without host supervision. To address this, we developed a microarchitecture that follows a hierarchical hardware organization, quad, block, tile, Cytem, and Cyto. It supports parallelism, and underlying the microarchitecture, we have enabled message-driven computation with deterministic execution model, where present or next address are routing on-chip data and present and next opcode are orchestrating computation. Overall, this is the outcome, messaging-based autonomous routing that can replace centralized scheduling with fine-grained parallelism, and it will enable host-free execution. In this section, we'll talk about the on-chip memory and data propagation, where we'll highlight our on-chip memory architecture, our memory capacity, different data propagation mechanisms. This is the typical system-on-chip architecture of an AI accelerators, and now you are familiar with it. In the previous section, we have covered that part, processing element array or PE microarchitecture. So in this section, our focus will be on the L1 global buffer and L0, like both are on-chip memory. Here, our contribution was to propose a 3-tier on-chip memory that collocates compute and storage within a predictable data propagation model. And we have framed this section around few guiding questions like how is Mavic's on-chip memory hierarchies is structured, and what is the memory capacity, what different types of data propagates via the on-chip memory, and which are the propagation mechanism we have used. To describe the hierarchical on-chip memory, we are taking a tile. A tile is a 4x4 Cytem array, and each Cytem has 4x4 cytos. Each Cytem has 16 cytos. So this is the off-chip memory. This is the system bus. The first on-chip memory inside the accelerator section is L2 tile memory. And after that, there are multi-level L1 Cytem memory. The Cytem memory, which is close to the tile memory, we'll call it level 4. Cytem memory, which is far from the tile memory, we'll call it level 1. And inside Cytem, there are 16 cytos. Each cyto will have one embedded cyto memory, L0. The tile bus size is 1024 bits, the Cytem 256 bits, and each cyto has 64-bit interconnects because our message size is 64. Now, if we look at the size, each cyto memory is 64 byte, each Cytem memory is 96 kilobyte, each tile memory is 0.125 kilobyte. In short, Mavic incorporates 3-tier on-chip memory, embedded cyto memory L0, Cytem memory L1, and tile memory L2. Now, to calculate the capacity, we have just scale up the idea. As you have already know that each quad will have 4096 cytos. So if we want to calculate the total memory size, 64 multiplied by 4096 bytes. For cytem, 96 multiplied by 256 kilobyte. And for tile, there are 16 tiles in a quad, 0.125 multiplied by 16 kilobytes. So overall, cytem memory L1 is occupying the highest size, then embedded cyto memory L0, then tile memory. Why it is occupying the highest size? Because ours is a message-driven execution model. Most of the time, messages will be executed or circle around the cytem. That's why intentionally it is made larger. And why the next priority is embedded cyto memory to improve our reuse. That we'll talk about reuse at section 4. Now, let me tell you the data propagation strategies. Before going to that, what type of data we propagate here? We propagate two types of data here, message 64-bit and weights 32 bits. How we propagate data? For message, we are using multicasting and hopping. For weights, we are using only hopping. So during multicasting, within one clock cycles, it will cover all the 4 rows inside a cytem. But during hopping, it will traverse one by one. So what is the word process? At first, from the off-chip memory, data will come to the tile memory. Then from tile memory, it will go to the top cytem level. And then from there, it will hop. And from each level of cytem memory, if the data is message, it will go to the computation unit. If data is not message, it will go to the data is weight, it will go to the embedded cytem memory. To summarize, two different data types, message and weight, propagate through 3-tier on-chip memory via two different techniques, multicasting and hopping. Now, let's look at how message propagation happens via multicasting. This is our level 1 memory. To reach from the tile memory to level 1 memory, we need 4 clock cycles. And now, as we are using multicasting, within one cycle, from the level 1 memory, we are covering all the rows of the hardware. Now, for level 2, it decreases to 3 because it is not the farthest anymore. And for multicasting, it will remain 1. So it becomes 2. And finally, the last one, it is close to the tile memory, it will become 1. Overall, the data propagation model can be represented as 1 plus number of tiles multiplied by 4. 4 is equivalent to the number of passes. Now, how data propagation happens via hopping? Let's say it is our level 1 memory. To reach from tile memory to level 1 memory, we need 4 cycles, like we said previously. But the change is here. Now, instead of covering all the rows at one go, we are covering one row at one time. And based on the hopping distance, it may vary 4, 3, 2, 1, like this. Now, level 2, again, hopping. Level 3, again, we are doing hopping one by one. Level 4, again, we are doing hopping. So overall, the data propagation model can be represented as 1 plus number of tiles multiplied by 16. 16 is coming from the number of passes. Here, the number of passes is 16. So now let's see the how weight propagation happens via hopping techniques. So you are familiar with it now. So level 1, one by one, it is going. Level 2, yeah, I'll cover it later. Level 2, then yeah, level 3. Okay. Now, the important point to notice here is that at first, uh, if you remember the size of the embedded cyto memory, it is 64 byte. What does 64 byte mean? It can hold 16 32-bit values. When you complete the 16 pass using hopping, 2 cells out of 16 cells of every cyto memory is being covered. So to complete the whole 16 cells, you need in total 128 pass. So Now the model becomes 1 plus number of tiles multiplied by 128. 120 is equal to 8 multiplied by 16. So up to now, we have seen how data propagation happens using the on-chip memory. Now we'll see how data propagation happens inside the compute fabric. And to demonstrate that, we are taking an example of matrix vector multiplication. Let's say it is our SITEM. Our first task is to load matrix A. During loading matrix A, the strategy we'll use is hopping. It will go one by one row. So that's why you are seeing here 4 clock cycles. And then the next task is to especially multicast vector B. When we are multicasting vector B, we are using those vertical buses. And at one go, the value is reaching all the rows. So 1 is coming to all the rows, 2 is coming to all the rows, and 3 is coming to all the rows. Then as soon as this is done, we'll do some multiplication. After multiplication, we'll do addition. During addition, we'll use the horizontal buses to propagate all the multiplication results and compute addition at the last column of the cycle. And finally, after addition, we'll offload the result for further computation, or we can send it to the memory. Then let's scale up the idea for matrix multiplication. Let's say we have 3 items. First task is to load matrix A. We are loading matrix A at every item. Now, matrix B, each column of matrix B will be multicasted to different items. Here, the first column 1, 4, and 7 is multicasted to item 1. Second column 2, 5, 8 is multicasted to second item, and the third column 3, 6, 9 is multicasted to third item. After multicasting, we'll do multiplication, and after multiplication, we'll do addition. During addition, we'll use those horizontal buses. We'll get the result, and finally, we'll offload the result. So overall, the summary of matrix vector and matrix vector multiplication is we are doing propagation and computation in an unified way and also parallelly. And we are doing everything without the centralized control using our on-chip message generation. So when we started this work, the problem that was in our head is like most of the accelerator gives us high throughput, but it becomes memory bound due to frequent off-chip data transfer. So our goal was to develop a localized message passing model so that we can reduce communication. To address this, we have proposed a data type aware 3-tier on-chip memory, and we have used 2 different propagation model for messages, multicasting or hopping, for weights, only hopping. And we have already shown our propagation model, they are predictable. Overall, we are achieving localized communication across multi-level on-chip memory that is helping us to sustain throughput and also break the AI memory wall bottleneck. Now, in this section, we'll talk about data mapping. Here we'll cover our software stack, our intermediate layer or Intuit framework, what are the mapping construct we are proposing, our proposed data flow, and we'll also give an example. During convolution, filter slides across the input image and perform some dot product. Followed by the dot product, it performs some accumulation, and finally you will get the result. And in this process, 3 tensors are involved: filter tensor, input tensor, and output tensor. If we look at the relationship, for example, number of images, it may present both input and output tensor. Number of filters, it may present both filter tensor and the output tensor. Like this. The key I want to highlight here is that the entire convolution space can be presented by 7 independent variables, as these 2 can be calculated using the other values. And to represent the convolution space, we have 3 different kinds of data flow. The first one is a straightforward canonical 7D loop nest, where each for loop is representing 1 independent variables of the convolution space. The second one is hardware friendly. It has introduced the concept of tiling and parallelization. And the third one is data-centric directives. It is more compiler friendly and it reveals the reuse parameters, it reveals utilization factor. So here, our core contribution is to develop a multi-level data reuse aware mapping strategy, and we have integrated those mapping strategy in our intermediate software layer to continue the compiler and the physical layer execution, and all being done under the deterministic message-driven execution model that we discussed at section 2. And we have framed this section around few questions like how can deep learning workloads be restructured into a spatial and temporal mapping, and how can computation and data can be co-scheduled, what is the function of our intermediate software layer, and how can on-chip execution continue from filter folding to image blocking to interlayer handoff without like host orchestration. So at section 2 and 3, we have covered our physical layer. So we have discussed the on-chip memory section. Also in the microarchitecture section, if we look at the very top of the software stack, there are frameworks and models, there are compilers. Compilers generate intermediate representation, but MABEC physical layer required binaries, and binaries in a certain format, in a message-based format. So to close this gap, we have developed the Intuit framework that has multiple components, for generation, resource allocator, task allocator, map construct, map compile and scheduling, also performance profiler. Overall, the Intuit framework is bridging the ML compiler and model graphs to a special temporal message stream for MAVEC execution. This is our Intuit framework. There are three main sections: input mapping, weight mapping, and hardware-specific address and instruction generation. So I will not cover all of this, but the key here is that there will be some input image tensor storing pair information, and it will create map instances that is apt for the map execution. Similarly, the weight mapping Intuit framework will take 4D filter tensor as the input, and it will create map instances that is apt for the map compilation. And this section, it has all the information about our underlying hardware, uh, instructions architecture, routing table, P array, our message format. So what it will do, it will collect the map instance for input and map instance for weight, and it will compile messages that can be executable in the MAVEC hardware. So overall, Intuit framework is generating MAVEC compilable mapping construct and compiling messages based on the spatial temporal execution plan. Our first mapping construct is the filter fold. So step one, here 4D filter tensor will be given as an input to the Intuit framework. For this example, we are considering a small filter tensor. NF number of filters is 4, number of depth is 4, filter size is 3 cross 3. The first task, it will convert the 4D filter tensor into a 2D filter tensor. Each row now will represent different filter. This is representing filter 1, this is representing filter 2, this is representing filter 3, and this is representing filter 4. Another thing to notice here is that filter indexes are mapped. Filter indexes are mapped in column reversed row-wise order. So you will start from the last column, and then you will go row by row. Last column, first row, last column, second row, and last column, third row. Then we'll move on to the next one, then next column. After flattening the 4D filter tensor to 2D filter tensor, we'll fragment it based on our available hardware resources. For this example, I'm considering a small hardware 4 cross 24. Based on these values, when we fragment it, we get two filter folds. Filter fold 1 is covering depth 0 and 1, and filter fold 2 is covering depth 2 and 3. So overall, 4D filter tensor is being transformed into a mapping computable mapping construct, and this mapping construct is filter fold. Now, second mapping construct is the image block. So the inputs are the image tensor, pad, and string information. So step 2 will follow some rules. If number of filter fold is 2, number of image block is equivalent to number of filter fold. In our example, in the previous slide, we have shown that number of filter fold is 2. That's why number of image block is 2 also. Again, number of depth covers in each image block is equal to number of depth covers in each filter fold. Filter fold 1, we have already seen depth is covering depth 0 and 1. Filter fold 2 is covering depth 2 and 3. That's why image block 1 is covering depth 0 and 1, and image block 2 is covering depth 2 and 3. Now, inside each image block, there will be multiple image fold, and the number of image fold will be equal to the output height. And inside each image fold, there will be multiple image column. Number of image column will be equal to the filter width. And if there is any overlapping columns, we'll only consider the unique columns. So let's see here. So for our example, number of image block is 2, and inside each image block there are 5 image folds. For the first one, there are 3 columns, 3, 2, 1 for both depth 0, depth 1. For the next one, it should be 4, 3, 2, 4, 3, 2 for both depth, but we are not considering 3 and 2 anymore because we have already sent those values and we will reutilize it inside our image fold. We will only keep the unique ones, that is 4. Same logic is applied to here, but 2 different depths, depth 2 and depth 3. Overall image tensor is being transformed into a mapping computable mapping construct. We'll call this mapping construct image block, and inside image block there will be multiple image folds. Now we will see how we are interacting with filter fold and image block in a pipeline fashion. The first step, program the P array or cyto array with a stationary filter fold. So ours is a 4x24 cyto arrays, and we are programming this with the filter values. And the next step, especially multicast an image fold across all hardware rows. So you are familiar with the multicasting terminology. So I17 is going to all the hardware rows. So one thing to notice here is that one image value is going to all the hardware rows, and different hardware rows are representing different filters. So one image value is being multiplied with different filter values, and in that way we are achieving a special reuse. Then we'll perform parallel multiplication. So this is giving us the property of parallelism. And after that, we'll perform hierarchical addition. So at first, column-wise addition, those 3 values will be added here. Then perform single depth reduction. Those and those values will be added here. And finally, multi-depth reduction. This value and this final value will be added. As a result, we get the first column of our partial sum fold. Then we'll do right shift by the convolution stride. Here the stride value was 1. So as you can see here, I17 is going there, I22 is going there. And then we'll repeat step 1 to step 4 to get the next column output, and we'll move on like this. So this is the final output from image fold 1. And if we want to quantify the number of shifts, it is 0 to q minus 1. Now, inside image block, there are 5 image folds, but I have only shown here 1. The point to notice here is that for other image fold 2, 3, 4, and 5, the filter fold will be remain unchanged. That means we are getting high level of temporal reuse, as multiple image fold are using single filter fold. So to summarize everything, filter fold and image block interact in a pipeline fashion where computation overlaps with the memory access. Now, this is a canonical 7D loop nest with weighted stationary data flow. Ours is a 3D abstraction. So with our first mapping construct, filter folds, we are covering these 4 values. With our second mapping construct, image block, we are covering these 3 parameters of the 7D loop nest. But we are calling it 3D because inside image block, there is another mapping construct, that is filter fold. Now, this is the data-centric representation of our data flow. If we look at the first construct, P cluster depends on the filter fold shape, and it gives us the value of parallelism and utilization. The next mapping construct, it is indicating that we are especially mapping filter fold, and our data flow is a weighted stationary data flow. The next one, multiple image fold are being utilized by a single filter fold. That's why we are getting temporal reuse. So temporal map, one image value is being multiplied by different filters at different rows. So it is indicating a special multicasting. So then inside the hardware, we are doing hierarchical addition. It is indicating a special reduction. And after collecting the partial sum results, we'll do one more addition that I'll show, or I'm going to show in the next few slides. So as a way, we are getting temporal reduction and how the data movements are happening, concurrent execution of two different loops from top to bottom. So overall, our proposed weighted stationary data flow unfolds spatial and temporal maps, enabling parallelism and high level of data reuse. Now, we'll see this example to connect everything. So for the input framework, what are the inputs? Neural network information and hardware information. As soon as it receives those information, it converts those things into mapping construct. For this example, there are four filter folds, filter fold 1, filter fold 2, 3, and 4. And you have idea now that number of image block is equal to number of filter fold. So that's why 4 image blocks. Inside each image block, there is multiple number of image folds. And inside each image fold, there are multiple columns. And we have already discussed those things. And then we have already discussed how the filter fold and image block interacts. And after interaction, we'll get some partial sum results. What we have not discussed, how these partial sums will be merged on chip and prepared as the input for the next layer. That is one question. And also at section 2, I've skipped the messaging based framework slide, and I told that I'll cover it after covering section 4. So this is kind of revision how one filter fold and image block are interacting together. So you have idea about the active columns, C0 columns, they are responsible for multiplication, and the reserved columns, C1, C2, and C3 columns, they are responsible for the multi-level addition. And ours is a weighted stationary data flow. Different hardware rows are representing different filters. And inside the cytos, we are loading the filter values, and under one image block, there will be multiple filter fold. In this example, there are 4, and image image folds will be shifted according to the convolution style. And if there is any overlapping column, we'll reutilize it instead of covering it inside our filter fold. Sorry, image fold. So now we'll see how all of these things happen via a particular message sequence. So this is our C0 columns. At first, we'll program the C0 columns with this. This is the incoming message. Then C1 columns 3, 7, 15, 19. We'll program this that kind of using that kind of message. Then C2 columns, that kind of message. And then C3 columns, there is multiple variation. If it is the first interaction, the message will be like this. If it is the last interaction, message will be like this. For the remaining interaction, message will be like this. So now the next multiplication messages come from the incoming side. As soon as this message comes from the incoming side, it completes multiplication, and also it generates some messages inside the fabric. And this message will be utilized as the input of the next column, C1 columns. And after calculating result, the C1 columns will generate this message. Those are the inputs for the C2 columns. And finally, after completing the C2 columns task, it will generate some messages for C3 columns, and as a result, we'll reach there. Then C3 columns will generate few messages. We'll see it after few slides. Let's summarize here. Filter fold and image block interacts, and during interaction, they do multi-level reduction. at first column-wise, then depth-wise, then multi-depth-wise, and as a result, we are getting some partial sums. Now, we have 4 filter fold and 4 image block. During their interaction, we'll collect 4 partial sums, partial sum 1, partial sum 2, 3, and 4. Now, what we'll do at first, for the first partial sum, according to the depth, we'll at first we'll update the Cyto values with the first partial sum. For the second one, we'll just add similarly for this first update and second add. And after that, we'll apply ReLU. During ReLU operations, we will have 2 objectives. One is to applying ReLU and change the value. Other is generate the message in such a way so that it can be utilized as the input for the next computation. So we'll see those things via message sequence. So we are here, we covered this part and this part. We'll start from here. So the first message is generates is update. The next message is generate is add for the last interaction. And for the remaining interaction, it will do some addition and streaming operation. And as a result, we will get some summation. After summation, we'll apply ReLU. When we applied ReLU, intentionally, I make it multiplication because I'm considering our next layer will be convolution operation. And as a result, when we are generating the messages, we are getting this message. Without host intervention, layer handoff can be performed because this message can be directly used as an input for the next layer. But the next layer can be many things. It can be 1-into-1 convolution also, then it doesn't matter, it will be multiplication. But if it is a max pooling, we'll use here intentionally comparison. If it is average pooling, we'll use average. So overall, what I'm trying to emphasize here is that messaging based framework executes the entire pipeline and handing off to the next layer. Everything is happening within the messaging based framework and without host intervention. So when we started this work, we have observed that existing data flows underutilize inherent spatial temporal reuse in CNNs because they convert the convolution operation into matrix multiplication and then perform matrix multiplication. But our objective was to find out the inherent reuse inside the convolution operation, like without sacrificing the parallelism, and implement it within our deterministic execution model using the messaging based pipeline. So to do this, we have developed the Intuit framework that can maintain the continuity between compiler and the hardware. We have developed a mapping strategy. We have 2 mapping constructs mainly, filter fold and image block. And using our data-centric data flow, we have calculated the reuse parameters, utilization, and several kind of reduction, also parallelism. And we have also shown using the messaging based framework how we are doing dynamic layer handoff. So the outcome is our proposed mapping strategy and data flow is covering multi-level spatial temporal reuse and within the deterministic message driven computation model. Now, in this benchmarking section, we'll mainly talk about our experimental setup, performance modeling, some simulation results, and some of the key performance metrics that we have measured. Now you're familiar with this figure. So we have covered the Intuit framework. In this section, we'll particularly focus on the performance profiler. So our performance reveals 93% P utilization, high spatial temporal reuse, more than 80% instruction are being generated in Fabric. For ResNet 50, we are getting 43.8 kilo inference per second, which is better than 2 to 10x better than state-of-the-art accelerators. So we'll try to cover those questions here. What is our experimental setup, key performance metrics, what does our result tell, and what is our competitive edge over other accelerators. So at first we have developed the RTLs for our architecture, microarchitecture. We have used Verilog there. Then for the initial level of verification, we have used Challenge River. Then for the ASIC implementation, we have used the cadence tools, and the PDQ we have used is TSMC 28 nanometer. So workloads that we have considered BG16, 19, ResNet 50, and a protein network. The key performance metrics that I'm going to highlight today are those utilization, some reduction, special temporal use, system throughput, and we have also done fair amount of comparison. So these are the key questions about performance modeling, our analytical model, but I'm not going to discuss it today. So these are some of the simulation results. We have done multiple verifications for programming, for matrix multiplication, and also for convolution. We have added a small example here. So the first performance metrics that I want to highlight is the average utilization. To calculate the average utilization, we have considered three different models: BG16, BG19, ResNet 50, three different hardware configuration: 16 by 16, 32 by 32, and 64 by 64. At each layer, individually, we have calculated the average utilization. If you like numbers, here it is. So for when the model is ResNet 50, for 16 cross 16 hardware architecture, we are achieving 73% average utilization. And for 32 cross 32, it is 85%. For 64 cross 64, it is almost 93%. Here is the trend for almost in every model. When the size is 16 cross 16, we are getting 73%. For 32 cross 32, 85%. For 64 cross 64, it is almost 93%. So our interpretation is that average utilization improved with P array due to better fold alignment and reduced fragmentation. The next one, we have used the same setup, three different models: BG16, BG19, ResNet 50, three different hardware configurations: 16 cross 16, 32 cross 32, 64 cross 64. Here are the numbers. So for example, when the model is ResNet 50, the hardware size is 64 cross 64. It is consuming 1.28 million clock cycles. So if we look at the trend for BG16, when it moves from 16 by 16 to 32 by 32, the speed up is 3.9x. From 32 by 32 to 64 by 64, the speed up is 4.9x. BG16, almost similar trend. For ResNet 50, when you move from 16 by 16 to 32 by 32, we are getting 6.4x speed up, and here 6.6x. Overall, our interpretation is that execution time decreases with larger arrays due to parallelism. Now the peak compute throughput, gigaflops or teraflops per second. So same setup, three models, three hardware configuration. Here are the numbers. So for example, for ResNet 50, when it is 64 cross 64, the in teraflops per second, it ranges between 1.7 to 2. We have also measured the peak. So when we measure the peak, for ResNet 50, we have seen that we are getting 4.1 absolute peak. So when I go back and check for that particular layer, it is perfectly aligning with that hardware architecture. That's why you are getting that much peak. Otherwise, it is other values are within the range. So to summarize everything, peak compute throughput is increasing with the array size due to faster fold processing. Now, a spatial reduction. What is the unit of a spatial reduction? Megabyte. And what is the significance of it? So if your data flow do not have that kind of property, you need to parallelize that much on-chip memory footprint. Same setup we have used: VG16, VG19, ResNet 50, and three different hardware configuration. Here are the numbers. For ResNet 50, for 64 cross 64 hardware architecture, we are getting 5.90 megabyte spatial reduction. If we look at the savings, when it moves from 16 by 16 to 32 by 32, savings is 2.48x. When it is moving 32 by 32 to 64 by 64, the savings is 2.86x. For BGG 16 and 19, the pattern is almost similar, 3x and 4x. So overall, a spatial reduction improves with larger array size as more columns and depth are processed concurrently. Now, a spatial reuse. So the same setup, three different models: BG 16, 19, and 50, and three hardware configuration: 16 by 16, 32 by 32, 64 by 64. So here are the numbers. So if we look at the for ResNet 50, when the hardware architecture is 64 cross 64, the special reuse was 0.236 on average. So if we look at the savings, so 2.26x and 2.81x. For BG 16 and 19, almost similar pattern, 2.98x and 4x. To summarize, a special reuse improves due to multicasting and shifting. Temporal use, same setup. Here are the numbers. So for ResNet 50, 64 cross 64 hardware architecture, we are getting almost 11 megabyte. So what is the speed up savings? 1.72x and 2.25x when we move from 32 cross 32 to 64 cross 64. For BG 16 and 19, almost same, 3x and 4x. So in our section 3, we have mentioned that our on-chip memory size is less than 100 megabyte. So it is our architectural constraint. Within that architectural constraint, how we are achieving much more better throughput than others because of these reuse properties and multi-level reuse and reduction properties. So to summarize this slide, temporal reuse increase with array size as more hardware rows are accommodating more number of filters. Now, this is an important observation. So from the very beginning, we are claiming that we are reducing off-chip traffic. To quantify it, we calculated the number of messages. In our architecture, there are three different kinds of messages: wait messages, image messages, and intermediate messages. Wait message and image message come from the off-chip side, from the host processor. So these are equivalent to off-chip memory access. And the intermediate messages are being generated within the fabric. So those are equivalent to on-chip memory access. Almost for every architecture, almost 80% time, 80% messages are being generated on chip, and that is validating our claim that we are slashing off-chip traffic. The next one, clock cycle breakdown by phase. So when we developed our analytical model for the throughput, there are mainly four phases: message transfer, operation, host to off-chip memory, and wait storing. If we look at the pattern, most of the time are being spent on the message transfer. So it validates that ours is a message-driven execution model. We are perfectly using the message-driven pipeline. Now, for ResNet 50, for this setup, FP32 of chip memory GDDR7 PCI X16 generation 6, number of cycles 4096 and frequency 1 GHz, we are getting 43.8 kilo inference per second. For BG16, we are getting 12.7 kilo inference per second. For BG19, 12 kilo inference per second. So overall, Mavic is sustaining high throughput by efficiently overlapping computation and message transfer. Then we have performed the design space exploration to gain more insight about our architecture. So when we have swept the hardware configuration and calculated the throughput, we followed a linear scale. So that is demonstrating the efficient utilization of compute and memory. Then we have also swept the frequency. For the frequency also, we are getting a linear trend. This one is interesting. When you swept different off-chip memory, there is not much variances. And that's exactly what we wanted, and that's exactly what we are claiming. We are more relying on the on-chip memory than the off-chip memory. So this is reflecting our on-chip data reuse and in-fabric message generation. So then we have also swept PCI generation and calculated throughput. So it is also following a linear scale. So it is indicating the efficient host device communication. Then to explore our potential for a different track for bioinformatics acceleration, we have taken an example of 5000 node protein network. We have used the PageRank algorithm, 100 iterations, 4096 cycles, and this much of computation is being done within 213.6 milliseconds. Now, even though our chip is not fabricated yet, based on our synthesis report and based on the TSMC 28 nanometer datasheet, we have estimated our silicon area. So our estimation is that for one core, which will incorporate 4 quads, it will be around 350 millimeter square. So to compare With the systolic architecture, we have targeted TPU and an improved version of the TPU, that is MESA. This is an academic paper. So we have observed how they have calculated their latency equations, and for apple-to-apple comparison, we have followed the exact same pattern and derived our latency equation. When we plotted, we have seen 1.5 to 2x latency reduction in compared to the systolic counterparts like TPU and MESA. We have collected the throughput of different accelerators for the same workload. So this is the baseline. For our case, we are getting 43800 inference per second, but for others, like for 10 student, it is getting 22431. For all are for same DNN model, but their precision is different. So we are almost 2 to 10x better than other SOTA accelerators. Now, then we have calculated the efficiency for 15 to 22 kilowatt power budget. This is our efficiency 2 to 2.9, which is reasonably better than the other few existing accelerators. Then we have collected the silicon area for other accelerators. So our estimated area was 3.364 millimeter square, and our on-chip memory size is less than 100 megabyte. So few things to notice here. If you look at the NVIDIA architecture, their on-chip memory is 40 megabyte, 80 megabyte. This is their silicon area, 486 millimeter square, 4814 millimeter square. So when you estimate the silicon area, three different things contribute. The first thing, on-chip area. The second thing, your arithmetic unit. And the third thing is the interconnection. And most significant part is the on-chip memory. So even though their on-chip memory is very low, their silicon area is very high. Uh, it indicates that they are putting more of the CUDA codes and they are doing things parallelly. And they're forced to do it because they are converting convolution to matrix multiplication. And as a result, they are they're deleting the inherent reuse properties of the convolution operations. If you look at TPU, their silicon area is reasonable, but their on-chip memory is almost 2x higher than us. So it indicates that they're putting a lot of effort on the on-chip memory, but as a result, they have to sacrifice their processing elements. So why they have to do it? Because of their control. Even though systolic architectures have some kind of internal reuse parameters, but because of their control to keep the data close to the processing element, they have for each layer, for pooling layer, for activation layer, for every layer, they have created different kinds of on-chip memory, and as a result, their numbers are increasing. So what I'm trying to say here is that even though we have not fabricated, but it is we can logically say that it has a strong area efficiency potential. So when we started, we didn't have any comprehensive evolution framework, as Mavic is an emerging hardware. So we have developed everything from the scratch. For every parameter, we have developed the analytical model according to our messaging-based execution pipeline. And when we calculate the result, so it is throughput is increasing linearly with the PER size and PCI bandwidth. It is indicating scalability. Almost 80% messages are being generated on chip. It is indicating less number of off-chip traffic. Architectural efficiency 1.5 to 2x lower latency than systolic architectures, and throughput is 2 to 10x better than other existing AI accelerators. And we are supporting multiple CNN workloads under one data flow. So in a way, we are getting the flexibility. So at the introduction, I have mentioned that our goal was to couple flexibility with the efficiency, and we are actually trying to do that here. So as a hardware architecture, Mavic is a decentralized parallel compute fabric which perform deterministic execution without host supervision. To do it, we are following a message-driven execution model where address helps routing and opcode helps task allocation. Our on-chip memory is a three-tier data on-chip memory that co-locates compute and storage. So within the on-chip memory section, we are using two propagating techniques, multicasting and hopping. So mapping is the brain of everything. It is governing data movement, computation in space and time, and it is exploiting multi-level reuse with parallelism and high utilization. So here we have developed the Intuit framework that bridging the gap of ML compiler and Mavic physical layer. So we are executing two mapping construct in a pipeline fashion. So, and finally, when we estimated our silicon area, it is 346 millimeter squares for ResNet 50, 43.8 kilo inference per second system throughput, 80% of messages being generated on chip, 2 to 2.9 kilo IPS per watt efficiency. So overall, our benchmarking result says that it is balancing flexibility and efficiency, and as a result, it is advancing the next generation AI hardware. So how we are thinking to take it forward? So first track that is in our mind is that we'll work on the microarchitecture development. In this section, we have already developed a vector multiplier that can perform 8 multiplication in a single clock cycle. So we have already developed RTL, and we have done synthesis under TSMC 28 nanometer technology. For the next track, we want to make our performance profiler more advanced. We want to integrate more parameters. So right now I have initially developed a energy cost estimation model in pen and paper. So we'll try to convert it to code. And the next one is that we want to explore Mavic's potential for bioinformatics acceleration. Previously, we have done a protein network analysis. This time, we are planning to do drug response prediction. So it was a long presentation, but I appreciate your attention and I welcome your thoughts.